Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. It's my delight today to introduce Kerman E. Fleming, who goes by Elliot. The E is for Elliot.
Yep.
And he's visiting us from MIT as a FTE hiring candidate who is, I think, very intellectually aligned with a lot of the work going on here at Microsoft. And he's done some really tremendous work as part of his dissertation, both on systems, FPGAs, and compilation to FPGAs. So I'm really excited to hear your talk, and thank you for visiting us.
Pleasure to be here. My name is Elliot, and today I'm going to talk about how we can scale programs to multiple FPGAs. So before we get started, I'd like to thank everybody that I've worked with. So basically, my advisors were Arvind and Joel Immer, and all of these folks here were involved in the papers covered in this talk. And here's a bibliography. So the compiler work is categorized under LEAP. AirBlue is a wireless transceiver project, and there are a few other designs presented. So let's get started. So basically, FPGAs have traditionally been used as ASIC prototyping tools or as drop-in replacements for ASIC. However, recently FPGAs have gotten quite large and also much easier to integrate into systems with PCIe, Ethernet, various IOs. And so now we can talk about designing big systems with FPGAs in them as a first-order compute with the goal to accelerate some algorithm. So we have some algorithm that we were running in software, but the software is not fast enough or maybe burns too much power, and so we want to run on the FPGA. Okay, the goal here is time to answer. So time to answer has two components. So one is, of course, accelerating the algorithm so it runs faster, but the other is also to reduce the amount of time that it takes an engineer to build an implementation. Okay? The second goal is functional correctness. So here, unlike in traditional FPGA flows where we cared really about preserving the behavior of the ASIC that we're going to produce, and we have to make sure it works right, otherwise we've wasted a lot of money on a mask set, here we only care about functional correctness. That is, that whatever answer we wanted to compute was computed correctly, and of course as fast as possible. Okay, so here are a couple of examples of this kind of program. So one is HASM, which is an emulator for processors. The other is AirBlue, which is a framework for building wireless transceivers, which are actually compatible with commodity hardware, so you can talk to your 802.11 base station. Okay, and again, the goal here is functional correctness for both of these codes, as long as we produce the correct answer within some high-order time bound, we're good. Okay. So now that we're writing programs onto FPGAs, we can ask the question, what happens if our program is too large, right? Remember that FPGAs, of course, are structural things. So we can, unlike in a general purpose processor, express a program that is too big to fit onto the substrate. So here we're laying down CPUs, and eventually we have too many to fit on the single FPGA. So what are we going to do, right? So one thing we can do is optimize. We can try to make our design smaller. That works to first order. Or we could go out and buy the biggest FPGA we can. Again, these are patches. But at some point, we have to use multiple FPGAs. And so what does that entail? One, we're going to have to partition our design. So here, there's quite an obvious partition, right? We just put, the CPU on the other FPGA. Two, we're going to need to map our design, this partition design, down onto multiple FPGAs. And then finally, we're going to have to synthesize some network between them. And of course, we can always do this manually. So we can take our engineers and have them implement this whole thing, and we'll run it, and it'll probably run quite fast. However, this can be tedious and error-prone, particularly if one is exploring a design space and needing to change the implementation. And the question is, can we do this automatically? Okay, so the remainder of this talk is going to discuss how we can achieve this goal automatically.
And automatic is non-tedious and error-prone?
Yes, non-tedious and error-prone. Okay. Right. Probably error-prone is the most important there. So before we get started on how the compiler actually works, let's talk about what we should expect when we map a design to multiple FPGAs. So more FPGAs mean more resources, and just like in a software program, when we throw another core or a better cache hierarchy to problem, we should expect more performance. Okay? So One thing in FPGAs, one metric of performance, of course, is the problem size that we can implement. And so what I'm going to show is that one of the examples actually can be 10 times larger when it fits on multiple FPGAs. So on a single FPGA, we can fit a 16-core model, and on multiple FPGAs, 2 to be precise, we can fit a model that can model up to 121 cores. So that's a 10x problem scaling for this particular problem. Also, when we give more resources to a problem, just like in software, we should expect it to run faster. This can happen for a number of reasons. For example, you get more DRAM banks on multiple FPGAs, but also since you're asking the tools to solve a simpler problem, when you partition a design, sometimes they can come up with frequency scaling as well. And so what I'll show you is that one of our examples can actually achieve a superlinear speed up when mapped to multiple FPGAs. So this is performance normalized to a single FPGA, and up is good. OK, so in summary, what can we expect? Design scaling, so we can get bigger designs when we have more resources, more FPGAs. We can get faster runtimes. And then finally, although I'm not going to discuss this, we can also get reduced compile times because, again, we're asking the highly nonlinear tools to solve simpler problems. OK, so the good news is, so again, our goal is to sort of produce these implementations automatically. And the good news is that multi-FPGA compilers exist commercially. So if they were good, we could stop, right? And they operate on arbitrary RTL, which is also good. Okay? The problem, though, is that they have to preserve cycle accuracy. So what is cycle accuracy, right? Cycle accuracy is a bijective mapping between the original RTL description, which was clocked, right, and whatever implementation we put on the FPGA. Okay, so in the FPGA implementation, there's a precise way to resolve the original behavior of the RTL. And so kind of what you can see here is that the model clock, which represents the original behavior of the RTL, is ticked in frequently. The FPGA clock, of course, is running very fast. And then between model clocks, we're doing some kind of communication between the chips in order to preserve this idea of cycle accuracy, right? Oh, and feel free to stop me at any time if you have questions. OK. So, and of course, you can see how this would be useful in ASIC verification because we want to preserve the behavior of the RTL. Because if we make any mistake in that translation, or if our RTL is in any way buggy, we could brick our chip. Okay? The problem, though, of course, is that cycle accuracy gives us low performance. So what you can see here is that the FPGA wants to be fast. It wants to run fast. But because we're having to preserve this cycle accuracy, we're actually going at a very low speed relative to what we could get out of the FPGA. Okay? And again, this comes from the need for distributed coordination. It also comes from the fact that there are very poor semantics here, right? Here, in maintaining cycle accuracy, we have to transport every bit just in case some logic might behave funny in the case that even if a bit is invalid, it was transported, right? So you can imagine here that if this data is invalid, right? So the control here is invalid, right? But we still have to transport all the data in case some point in our circuit might misbehave, right? So we could have some random data vector here, right? But that might cause a bug in our design. We don't know. And if our objective is verification, of course, we need to preserve that behavior so we can fix it. Yeah?
I'm sorry if this sounds like a moderately hostile question, but it seems to me like you're setting up a little bit of a straw man here.
Sure.
You're saying, well, I want to synthesize RTL to a large logical FPGA, but then I'm going to partition it to multiple ones, and I've got, comparatively enormously slow communication and low bandwidth between them. Mm-hmm. And so that won't work well unless I partition the design.
Well,
semantically said. That seems like it really does seem like a straw man, because there's no hope of getting to that magical point where you can partition any design and have it run at your FPGA or your
precisely, and that's why we're not going to partition any design. We're in fact going to restrict designs in a way that leads to good partitioning. So basically, we're going to give programmers a new primitive, which we'll talk about in the next couple slides, that will enable them to describe designs in a way that we can easily map.
Okay.
All right. So we'll see how that works. Okay. So again, here we're preserving cycle accuracy, but remember what I said, the goal of this new use case for the FPGA is functional correctness. As long as we get the right answer, we're happy. Okay? So the question is, do we actually need to preserve all of this cycle accuracy? The answer, of course, is no. So what I'm going to advocate is this new style of design called latency insensitive design. The basic idea here is that intermodule communication occurs only over latency insensitive channels. The idea is to decouple the behavior of different pieces of the design, from one another so that we can change their implementation. Okay? Changing the timing behavior of a module, then, does not affect the functional correctness of the design, right? As long as the data flows between the modules and that data flow is preserved, then the behavior of the design will be the same, the functional behavior, right? Of course, the timing behavior will definitely change. Okay? Many hardware designs already use this methodology, right? So most hardware designs are described in terms of these FIFOs explicitly, for the obvious reason that there are many unpredictable latencies in hardware designs. And of course, hardware designers also want to do design space exploration. Okay? Why? Again, improve modularity, improve design space exploration. And today, what we do is we simply insert FIFOs, guarded FIFOs between the modules and the design, right? And of course, we don't enqueue data into the FIFO unless there's room to enqueue data. We don't dequeue unless there's actually data in the FIFO. And we express our design in those terms. This is a very simple model. Okay? So let's think about that a little bit. So what I said was that we could change the behavior inside of any module in any way we wanted while preserving the functional correctness. But what this implies is that we can also change the behavior of the channels themselves. So if I can change the behavior of the channel and I have a design described this way on an FPGA, mapping into two FPGAs is straightforward. I simply stretch the channels between the boundaries. And of course, logically, these are still FIFOs. Okay? But there's a problem. I can have lots of FIFOs in the design. And not all of them may have this property, right? Because remember that a compiler, an RTL compiler, sees only wires and registers. It can't even tell probably that there's a FIFO here. Okay? Right? So semantically, it may see some wires and registers with some logic, but it's very difficult to even determine that there's a FIFO. Okay? And additionally, of course, reasoning about cycle accuracy is difficult. Okay, so it's very hard in these things even to decide whether or not it's safe to add an extra pipeline stage in a FIFO. But the programmer knows about this property, this latency insensitive property. He expressed his design this way to sort of get the benefit of modularity, right? So what are we going to do? We'll just give the programmer a syntax to describe these kind of latency insensitive FIFOs. Yeah?
Can you give me a more precise description or semantics of what you mean by latency insensitive? Okay,
so what I mean is so first let me clarify that latency insensitive does not mean that we don't care about latency, right? So this is a common problem with when we use the term latency insensitive, right? What it means simply is that we're free to change the behavior of the FIFO. This will come up. All right, so we'll get to it in a couple clicks, but basically, we're free to change the behavior of the FIFO, and the programmer is asserting that they've described the rest of their design in a way that permits us to make this change. Okay? So, for example, they won't try to enqueue data into the FIFO if the FIFO is full. So kind of they're leveraging the back pressure on both ends of the FIFO. Okay? Again, this is not the only way to write a FIFO in your design. You're always free to use the register and wire FIFO.
So is latency insensitive then defined in terms of this particular implementation technology of FIFOs? I mean, is that the only way to characterize it?
I don't think so, but it's hard for me to imagine any other way of characterizing it.
Asynchronous logic?
What's that?
Asynchronous logic?
Yeah, you could think of it that way, perhaps. So that's fair. You could think of it as asynchronous logic in that whole field. That's sort of what we're doing here. Again, compute is happening on data flow tokens. And we're decoupling the notion of clock from compute. I mean, that's the fundamental difficulty, right? Is in cycle accuracy, clock is a first order thing. Here we're trying to remove the notion of clock so that we can perturb the design in some ways that are beneficial to the programmer. Yep?
So indeed, if you do have these enqueue on one end and commands on one end and the data valid pops something from the queue on the other side, how can you have a latency insensitive channel that you can't stretch?
So the question is why aren't all FIFOs latency insensitive?
Exactly.
Right. The simple reason in this is because you may make assumptions about the particular implementation of a FIFO. For example, you may make the assumption that this FIFO has a depth of 1, That is, when I enqueue something into it, it will be full. And that will you'll use that control logic to determine some other things in your pipeline. So for example, you may say, if this thing is full, I will issue some other request.
So FIFOs don't have proper flow control.
No, the FIFO may have proper flow control, but you may make some assumption about the buffering, for example. You could also make an assumption about the latency. But I think the more common case, at least in the designs that I've worked on, is you make some assumption about the depth of the FIFO. For example, that it has 1 or 2 buffer slots, and you write other logic to expect that. And so actually adding more buffer slots than perhaps 1 or 2 would break your design, because that assumption that you baked into the logic is no longer true, right? I mean, you could imagine having a single entry FIFO with flow control, not full, not empty, right? And then using that assumption that it's got a single buffer slot in it to actually implement some other logic. I mean, people do that. The basic issue is if you allow people to leverage that assumption, then it makes it very difficult to make the kind of changes that I'm going to propose in the next set of slides.
It seems to me that the thing that you want is to find large regions of code that have no recurrences.
Large regions of code that have no recurrences.
Well, in other words, if think of it like a pipeline. You're doing partitioning, and the degree of latency and sensitivity is the amount of compute you can do that's decoupled through a FIFO before you have to go back and close the loop.
That's right. So feedback.
Right.
That's right.
And we've known this from pipelining for decades. And so if your tools can analyze your design and find the partitions that don't talk back to other regions, do some sort of graph partitioning.
Right.
Then that's how you can actually map this. Are you taking an approach like that?
So we haven't studied mapping, right? So mapping has not become a problem for us yet. I'll talk a little bit about how we do mapping, but it's quite naive. But you could imagine some approach like that being necessary as a refinement to this.
Okay.
However, I'll also point out that generally speaking, even if there is feedback in a pipeline, very often hardware pipelines will have a pipeline depth that is sufficient to cover the latency of inter-FPGA communication. This is certainly true in DSP algorithms. I think it'll be true in others. So for example, HASM, because of the way it's implemented as kind of a time multiplex pipeline, will actually have enormous potential to hide the latency with useful work, the latency of communications.
Sure. I'm just thinking about arbitrary applications and,
sure.
and a general underlying approach.
Yeah. So generally speaking, yes, you would want to try not to partition across feedback paths too often, I think. But we don't have any way of doing that automatically now. Okay, so anyway, here's the syntax. Basically, one frames one's design in terms of sends and receives. And at compile time, the compiler will choose an implementation. One example of an implementation is just the vanilla FIFO that you could have written anyway. Okay? On the other hand, you may choose to synthesize a complicated network. Again, depending on placement and other design goals. All right? And again, here we have an explicit programmer contract. When the programmer writes down the send-receive channel, right, he's willing to accept unspecified buffering and unspecified latency, right? And he's guaranteeing that he's written his design in a way that will admit of that choice by the compiler. So of course, the programmer can write a buggy design, and the compiler will happily generate a buggy implementation. It's more of a programming tool in that sense. Okay? However, generally speaking, we found that this primitive is pretty easy to use. Often you can take FIFOs in your design and just substitute them out. So it can be a simple substitution. And this has been our experience for most FIFOs, except the ones which I was describing to you in the back, wherein you're using them for control, the FIFO, the depth of the FIFO for control. Okay, so now we kind of talked about a syntax for describing latency insensitive designs. And we've seen that latency insensitive designs can, at least in theory, be mapped to multiple FPGAs. So now let's talk about a compilation flow. So we'll now discuss a compilation flow to do that. And then afterwards, we'll talk about how we synthesize networks between FPGAs. Okay? So what we're going to do is we're going to start out with an arbitrary RTL augmented with latency insensitive channels. So what we've got here are little state machines. They could be any RTL, or they could be software for that matter. It doesn't necessarily even have to be an RTL. connected by latency-insensitive channels shown by the dotted line. So we just have some graph. Okay? And again, I mentioned that to produce a multiple FPGA implementation, we have 3 phases. So the first, we have to build some graphical representation of this, which we can partition. Okay? Then we're going to have to take that partitioning and map it down onto some network of FPGAs. Okay? And then finally, we're going to have to synthesize a communications network carrying the yeah, sorry.
Who's responsible for establishing that the RTL behavior doesn't change when the latency of the channels changes?
The RTL behavior may very well change. Absolutely. The point is that you're asserting that those behavioral changes are not going to impact functional correctness. Okay? Again, the RTL behavior will absolutely change in much the same way that your RTL behavior would change if you interposed a level of cache hierarchy. Right? It will change. But it's the programmer's job to ensure that these changes don't perturb the functional behavior of their design. In practice, this is not a very difficult thing to do.
When you say RTL behavior, are you talking about timing, interleaving of timing events? Or are you talking about
timing, yes.
Yeah, okay.
No,
yes.
I'm thinking correctness. I mean,
oh yeah, correctness
could
could be
the same bits even delayed if the channel starts.
Yeah, no, absolutely. You know, if you wrote a bad design, or at least a bad design in terms of you know, this property, right, you could very well get an incorrect implementation. Although, of course, I'll ask the question, if our design was too big to fit to begin with, how would we have implemented a transform to preserve that correctness? Well, we would have just, we can do it, right? There are tools that do it, but you pay all your performance, right? So you lose order of magnitude of performance to preserve the property, right? So this is the trade-off that we're making here, is instead of preserving that exact timing correctness of the original RTL, we're giving freedom to the designer to express points at which that behavior may safely be changed. And we're going to leverage that. Right. Yep.
By RTL, you mean Verilog or netlist?
So this is a Verilog. So, well, for full disclosure, we actually implemented BlueSpec for a number of design choices, mainly because BlueSpec is easier to augment with compiler-like features, just like Haskell, its predecessor. But you could imagine these RTLs being Verilog also. So you could think of this as just putting these send and receive endpoints into Verilog. That's certainly admissible. OK. And then finally, what we're going to do is, given this sort of implementation, we'll produce an RTL for each FPGA, and you can run it through the backend tools to produce implementation. OK? All right. So the first thing we do is we're going to construct a graphical representation that we can partition. Of course, remember that the only thing we know how to modify are these latency-insensitive channels. And that's going to kind of give us this graph structure over here, where we have blobs of RTL connected by latency-insensitive channels. We call these latency-insensitive modules. Although I've shown RTL here, again, it is possible to put whatever kind of computation you'd like in there, including software, right? As long as it ascribes to the latency-insensitive channel communication model. OK? And then what we're going to do is chop up the design in this way and map it down onto a set of FPGAs. OK? And again, the vertices are latency-insensitive modules, and the edges are latency-insensitive channels. And here's an example of the syntax here. So we have some channel A, and it induces the edge here. OK? All right. So now that we've got that representation, our next objective is to place it down onto a network of FPGAs. OK, so the first thing we need to know is actually what the topology of it. Yep.
So if you go back to the previous slide,
sure.
The borders between these devices assumes that I'll have one cycle data out to data in.
No, not at all.
That every cycle I can produce data, and such that the bandwidth between each of the devices is full bandwidth.
No, not necessarily.
Okay.
Again, these are just queues, right? So if you don't push anything into the queue, there's no communication at all.
Fine. If I push something into the queue every cycle,
sure,
and the interconnect between, say, the block A and the block B is insufficient to run at that speed.
Yep.
So, for example, the time multiplexing, that you described very early in one of your very early slides is often done because the bandwidth externally is so much smaller than the bandwidth internally.
Yeah, that's sure. And we'll do time multiplexing in this approach too, but we'll also have back pressure. Okay, so if if the bandwidth, oh, sorry, I hit the wrong button. If the bandwidth on C is insufficient to carry all the traffic between A and B, then A will stall. A will get back pressure, and A will stall. The hope is, of course, that as things scale up, you'll get more and more bandwidth. But it is a problem, right? If C is enormous, if C is 10,000 bits, then yeah.
So how do you know how many pins to allocate between point A and point B?
So we'll talk a little bit about that when we talk about compiler optimization. But generally speaking, first of all, the conception that these are pins carrying traffic between FPGAs is a little bit mistaken. So actually, they turn into these high-speed transceivers, right? So actually, there aren't pins at all in some sense. But we will talk about how exactly we allocate the bandwidth of the transceiver, in a sort of intelligent manner, perhaps in 10 slides. Well, maybe less than that. Yep. Okay, did that answer your question? We'll talk about bandwidth allocation at some point in the future. All right, so anyway, we need to know what the physical topology of FPGAs is. This is a little syntax for describing that. So basically, we have two FPGAs, FPGA 0, FPGA 1, and they're connected by bidirectional channels. And of course, you could scale this up to have whatever system topology you would like, even though I'm only showing a short example here. Okay, and so this is the physical system where we have two FPGAs, and they're connected by some high-speed transceivers. Okay? And then what we'll do next is we'll map the modules based on area. So of course, you have to have a feasible implementation, but also you want to minimize communication between the FPGAs. At least ideally, we would have some algorithm that did this automatically. And so you get some mapping, like this, where A and B are on one FPGA and C and D are on another. But currently, we require user input. So the user is going to have to tell us which module goes where. Okay, now, of course, an important future work is doing that automatically. Okay? I'd like to point out at this time that this configuration file is the only thing in the design that differentiates a single FPGA from multiple FPGA implementation, or even a 3 or 4 or whatever FPGA implementation. This is the only part of the input to the compiler which is changing. Okay? The program itself is fixed, which is, of course, an important property. All right, so now that we've done this mapping, we have to synthesize a network. So basically, this entails choosing an implementation for each of these channels. Local communications, of course, just turn back into our vanilla FIFOs. So they're just this sort of ideal high bandwidth interconnect, right? However, remote communications will actually go through some kind of network hierarchy, okay, which we will synthesize based on the program. I'll talk about that in the next set of slides. Okay? So all of those channels will be tied down to some router, which will manage the inter-FPGA interconnect. Okay? And of course, this link will appear as a FIFO, but the routers themselves will be quite complicated. Okay? So now we've seen basically a flow of how we can get from RTL to a multiple FPGA implementation. And now we'll talk about specifically how we build the routers. Okay? So here's a kind of a cartoon of the network architecture, right? So basically, the user program is seeing FIFOs with back pressure. Okay? And of course, these FIFOs are going to be multiplexed onto the router infrastructure. Okay? So although this programming model is quite simple, the hardware to support it is actually quite sophisticated. So basically, we have this automatically synthesized layer of network hierarchy. So the first layer is marshalling. So we have to be able to handle some wide links and convert them into a fixed packet size. Okay, then we have to have some virtual channel buffering to ensure that channels don't block each other. Okay, and to ensure deadlock freedom. And then finally, to improve the parallelism, we'll actually run multiple lanes across the link in order to try to soak up as much inter-FPGA bandwidth as we can. Okay? Is this clear? All right, so the first thing we do is channel marshalling. So in the original user program, of course, the user can describe whatever data types they'd like to be carried between FPGAs. But the network width is fixed, so we have to introduce some layer to packetize the data types. So for very wide data types, of course, you just do the shift register. But for narrow data types, we'll actually just pack everything into a single network word. And we will do this based on the links, right? So this will be automatically chosen by the compiler. And this is actually important because remember, we're working on hardware designs. And of course, hardware designers are always trying to economize on bits. And it turns out that in many hardware designs, the width of the channels is actually quite narrow. This is an example from Haysom, and what we see here is basically that the overwhelming number of channels are narrow. Okay? So the next layer is channel multiplexing, right? So the good news is that most channels actually don't have a lot of activity. And remember, we're only carrying data between FPGAs when data is explicitly enqueued. So if there's no activity, then there's no bandwidth consumed. Okay, the bad news, though, is we don't control message creation and consumption. And this can lead to deadlocks because we have a shared network infrastructure, right? To see how that can happen, let's look at an example. So now we need both A and B to do the star operator. A sends a value. And of course, A is going to send again, right? And you know how this works, right? So now B is going to send something which we actually need to proceed. And of course, it's got head-of-line blocking. So we're deadlocked, right? How do we solve head-of-line blocking? So one option is we could try to compute the dependencies and do something intelligent with virtual channels. But in reality, we'll just give every channel its own virtual control. Okay? How do virtual channels work? So this is going to be deadlock-free via the Dally-Seitz theorem because, of course, we've broken all the channel dependencies, right? Since each channel has its own virtual circuit, then we can't have a deadlock. Okay, so how does this work? Well, now A sends, but A doesn't have any more flow control credits, so it can't send again. So now B will send, and of course, it's now out of flow control. Now the operation star can proceed, and we'll send flow control credit back, and A can proceed again. So it's very simple. Okay? This is kind of how flow control works in general. Now, of course, we have some options in implementing this. So one option, of course, is to have very small buffers. Small buffers are inexpensive. Of course, there's a problem because inter-FPGA latencies can be quite long. And so if we have small buffers, then if there's a hot path between the FPGAs, then we can stall. Okay? On the other hand, large buffers are expensive. So if we just give a large buffer, so say we give 8 registers per channel, then we end up using most of the area of the FPGA. And of course, this is problematic because what we want is the user program to have most of the area of the FPGA for its own implementation. Okay? So what are we going to do? Well, so observe that the channel connecting the FPGAs is actually serial. So what that means is that we're basically getting 1 data word per cycle. Okay? What that implies is that the store for all of our virtual channels can also produce data at 1 word per cycle, and will still satisfy the full throughput via Little's law. Okay? What this means in practice is that we can use a serial structure, specifically BRAM, to store all of these virtual channel buffers. And what that means is because BRAMs are quite dense, we can actually have enormous channel buffer per virtual channel. And we'll still be deadlock free because the virtual channels don't block each other in this shared structure. Okay? No? Yes? Maybe? So basically, right, what we'll do is because this is serial and the SRAM is serial, we won't lose any throughput, but we can have a very deep buffer per channel, which allows us to cover the latency of the inter-FPGA links.
So you're saying you're using block RAM with a single write port?
Yes, single write port. That's right. Single write port, single read port, so we get full throughput. Okay, a little bit of latency maybe, but we get full throughput. All right, so this is what the multiplexer microarchitecture looks like. So basically, again, as I said, we have all the virtual channels mapped down onto the SRAM. Okay, and then we have some bookkeeping bits out to the side also mapped into LUTRAM. What's that? Oh, okay, so data comes in, right, stored into the BRAM, and then we have some arbiter that selects which virtual channel we're reading out of based on the bookkeeping bits. Okay, and the great news here is that even if we give enormously deep buffers, more than 100 buffers per channel, we use only a small percentage of the FPGA for typical designs. And this allows us to scale the size of our implementations. So we can actually, instead of, we can have connections between several different FPGA devices without overwhelming our area usage. Okay?
How do you determine whether you should be using this, this architecture or the previous architecture based on, how do you do the allocation?
What do you mean?
Because this has, of course, the issue of, you are doing time multiplexing.
That's right.
By its very nature. So how do you know when you can afford a non-time multiplex architecture versus a time multiplex?
We'll get to that in a couple slides, I think. Okay, so the last level, so at this point in time, actually we'll get to it in this slide. So at this point in time, we have a fully functional router. So we could just lay this thing down and we'd have a working multiple FPGA implementation. The question is, can we do better? And the answer, as you allude to, is yes, we can do better. Okay, so in order to do better, let's kind of look at the properties of user designs. So specifically, what the widths of the channels look like and what their traffic looks like. And what we see here is that, of course, as I already mentioned, channels are narrow, and also that these narrow channels can have some high occupancy, right? So ideally, what we want is to sort of service these channels as best we can. Okay, so user designs have pretty low clock frequency and narrow channels, whereas the inter-FPGA physical layer is very fast and is hundreds of bits wide as a result. So of course, you have to do this clock frequency sort of gearboxing, right? So if the user design is running at 50 megahertz and the inter-FPGA PHY is running at hundreds of megahertz, then we have to sort of multiply up its width. And you end up with a few hundred bits per cycle of data that you need to stuff into the PHY in order to get full bandwidth. Okay? And what this is telling us is basically that in the presence of all these narrow channels, single channel at a time is very wasteful. So if we just do a naive time multiplexed approach, we're going to waste a lot of bandwidth. Okay? So how do we do better? Well, we'll have multiple lanes. Okay? And then we'll share the bandwidth. Okay, so how does this work? So basically what we'll do is we'll instantiate several multiplexers on top of the wide PHY, okay, forming lanes. So here we have one multiplexer, two multiplexers, three multiplexers, all on top of the same wide physical layer. Okay? And these can all go in parallel. Okay? So we can recover some of the parallelism of the system. Okay? Right? So we have some time multiplexing. Of course, these remain time multiplexed, but they can all transmit data in parallel. Okay? So now that we have the capability of adding these lanes, we have to ask the question, how many lanes should we have, and how do we allocate channels to lanes? Right? So these are free parameters in our router architecture. Okay? So we could look at the dynamic behavior. Of course, ideally what you would not do is you would not allocate two channels which are constantly being in-queued at the same time to the same lane, right? Because then, of course, they're fighting each other for bandwidth. Okay? We can't really reason about that behavior at this point in time, although maybe with some better program analysis techniques we could. But what we can do is observe aggregate channel loads. So what we can do is instrument the design and look at the traffic across each of the channels in the design and try to do something with that. Okay? The idea being that what we'll do is we'll minimize the maximum load on a given lane. Okay? So we take that maximum load as kind of a measure of how fast our program is running, assuming that it's communication bound, and we'll try to make that as small as possible. Okay? Unfortunately, this is a processor scheduling problem, or at least it turns into a processor scheduling problem. It's NP complete, but there is a good heuristic longest job first. So how does longest job first work? Okay, so what we have here is a set of channels in a program that we're going to route between two FPGAs. The height of the bars represents the loading, that is the absolute amount of traffic across the channel, and the width represents the physical width of the channel. So you may have some channels which are wide and some channels which are narrow. Okay, they produce more or less amounts of traffic. Okay, so the first thing we'll do is sort according to load, and we're going to try to make the situation the best for these heavily loaded links. Okay, because of course, what's that?
Is it the right way to think about this, that the width represents the packet size and the height represents rate?
The height represents total traffic, right? Which could represent rate, although, you know.
If you've already taken out packet size, then isn't total traffic divided by packet size the same as rate? Packet rate?
Yes, across the run of the program, right? But you may have some. I guess what I'm trying to say is there needs to be a distinction drawn between the aggregate behavior across an entire run and dynamic behavior, right? And so we're not.
Is that distinction just burstiness?
Yes, burstiness. That's right.
So how are you capturing burstiness?
We're not.
That's really where I was going.
Right. Yeah, we're not capturing burstiness.
Okay.
Right. That's right. So I mean, obviously, you know, if the total program runtime is something up here, then the rate may be low, but you may have burstiness, and that might perturb your router architecture. But I'm not trying to capture that at this time. Okay. So anyway, basically, what we'll do is we'll take our heaviest loaded lanes and heaviest loaded channels and synthesize lanes for them. Right. So 1, 2, 3 for the three heaviest loaded channels. Okay. And then we'll allocate those heavily loaded channels to the lanes. Okay, now with the remaining channels, we'll try to load balance, allocating the channel to the least loaded lane. Okay, so now we put this one here, and we'll put this one here, and so on. And what we've got is basically load balancing. Okay, so on average, the total amount of traffic across each lane is more or less equal. Okay? And yep.
Question, are you taking into account the width as well in this allocation?
That's
or
right,
just
yes,
the
yes,
load?
yes. Because if we put a sort of, although we're not doing it here, if we put this fat channel on a narrow lane, then its traffic will change. So yes, we actually do account for that. So when we make the choice, we change, so you can, of course, because you've kind of statically allocated the widths, you can see how much traffic will be across each lane. Yep.
So this has to come from simulation, right?
Or a run, yes. Yes, it's feedback-driven compilation.
And
That's right.
that depends on how you set it up.
That's right. So it's workload dependent, absolutely.
So it's on one FPGA. They simulate on one FPGA.
Oh no, you could simulate it on 2 FPGAs. We'll instrument all the channels for you and find the
Okay,
loads.
so you make a pre-mapping, try.
That's right. So basically, you're always free to synthesize a crappy network, and ideally the loads will not change very much. Or you could do it in simulation. Of course, that's an infinite capacity FPGA. Although generally speaking, for most of these designs, they're of a sufficient size that simulation is not your most attractive option because you can't really run a large enough workload.
Are you going to talk about topological mapping of the FPGA network?
What do you mean by that? So this idea of perhaps adding root throughs to handle strange physical topology relative to logical topology?
Strange is perhaps pejorative.
I see.
I mean, you're assuming that your producers and your consumers are on adjacent FPGAs.
No, not at all.
Okay, and so
Not
if
at
your
all.
producers and consumers are not on FPGAs,
We'll add root through.
you add root through.
That's
and,
right.
And then now you're talking about a routed network,
That's right.
and now your virtual channel approach is a little bit trickier.
No, not
because-
particularly, because again,
Well, let me finish the question. If you have with the observation, if you have a shared link
Mhm.
with a direct communication and then a route through,
yep.
all right, you've got to worry about both sets of virtual channels.
If you were trying to do something clever, I could imagine that being the case. However, what we do is at each inter-FPGA crossing, we will give a new virtual channel. Okay, so basically, the virtual channels are only handling deadlock-free on that single inter-FPGA link. So basically what would happen is you bounce, what's that?
Single hop.
Right.
So you in some sense turn it into a statically routed network, and
Yep.
you better hope that there are no dynamically routable paths.
You could have a better implementation perhaps if you had some capability to do dynamic load balancing. But, you know,
Well, no, it's not just load. We talked about this this morning.
Hmm.
If I have a failure
right.
and I want to remap, you know, a FPGA's role to another FPGA.
Sure.
Now all my routes through your network change, and the virtual channel
Sure.
allocation changes.
That's right.
And it doesn't sound to me like you've provisioned for that dynamically.
No.
Right.
But it's, again, the virtual channels are so cheap that it wouldn't be beyond the realm of possibility to have spares. I mean, again, you know, these things are very inexpensive. I mean, really, the cost of a new virtual channel is just the cost of adding extra space in an SRAM, and the SRAM has, you know, 64 kilobytes of space. I mean, once you have one of them, right, you actually have a lot of space.
I think maybe for the problems you've allocated, the packet sizes are relatively small. But if you start having large packets routed through these virtual channels, even the amount of SRAM you're talking about can get really high.
Maybe.
Yeah.
Maybe.
If the packet is 4 kilobytes, for example.
Yep. Of course, you could break that packet up into chunks and just do channel allocation on chunks.
Yep.
Could certainly do that.
So,
Yep.
related.
And in fact, that's what we would do. We would marshal it and do flow control in the marshal it.
So as you increase the number of virtual channels, do you see the logic you have for scheduling the virtual channel and deciding which one to send out? Do you see the overhead of that going
Yes,
up
so it does go up.
drastically?
That's right. It does go up. And in fact, depending on the number of virtual channels, we can choose different arbiter architectures. So we have several layers of pipelining. So of course, if you have a handful of virtual channels, then you get single cycle scheduling. Otherwise, you have to do 1 or 2 cycle scheduling. But 2 cycle scheduling goes up to several hundred lanes, so it's scalable. I mean, you could even, if you wanted, add a 3rd level of hierarchy there. But again, it's just dropping it in, right? And the compiler can choose based on the number of virtual channels. Yeah. Okay. So what happens when we do this optimization to a real program that is HASM? So here we have the naive implementation of HASM, right? And again, up is good. So up is aggregate MIPS for the simulation. And so when we do this longest job first algorithm, we do get some 10% performance gain. Again, here what we've done is we've eliminated sort of collisions between packets, right? So in HASM, there were perhaps tokens being generated simultaneously, and having more lanes removes some of that effect. I'll point out that HASM is actually not communications bound. So it uses only about a third of the bandwidth between the FPGAs. So that's why we don't get some higher throughput, because HASM actually isn't stressing the network. If, of course, you use some kernel, some kernel which is in fact producing a large amount of traffic, then you will get linear speed up as you scale the number of lanes, as you might expect. Okay, so now we've talked about sort of how we synthesize the inner FPGA network and how we actually describe and implement designs that can be partitioned across FPGAs. Now let's talk about a couple examples. Okay, so we'll look at two case studies, AirBlue, the wireless transceiver, and HASM, a simulation framework for modeling multi-cores. Okay, so the basic idea of AirBlue is we want to implement wireless transceivers such that we can operate on the air with commodity equipment to test out new protocol ideas. So this works well if the protocol is simple, like 802.11g, but newer protocols, particularly those with MIMO, of course, require much more area, and so they don't fit into a single FPGA. And that also includes the need for multiple antennas. Okay? So what do? Well, we just throw another FPGA at the problem. So we go from one FPGA and an RF front end to two FPGAs and an RF front end. It's that simple. Okay, so the baseline 802.11g implementation looks like this. So you've got a TX pipeline and RX pipeline. And what we want to do here is implement some new algorithm, spinal codes. Okay, spinal codes is some new error correction algorithm. Okay, the problem is it's much larger than the existing. It's new. So it was at SIGCOMM in August. It's actually quite good. So it's actually better than Turbo in most respects.
Scared.
Oh, yeah. Maybe talk offline about how the name came about. It wasn't my choice. I always think of Spinal Tap. Okay, so anyway, basically the problem with this code, though, as good as it might be, is that it's much larger than Viterbi, and so we exhaust the area of the single FPGA. Yeah?
And it's asking for ignorance. Is baseband mean anything until you start playing with radio frequency?
That's right. So basically, it's the part of the wireless transceiver between the RF and the MAC working on packets, right? So it's the thing that's taking that baseband signal and turning it into packets, right, with error correction and various other algorithms running. Okay? So anyway, of course, as you might expect, we just simply partition across two FPGAs, right? Again, these little FIFOs here are latency insensitive channels. And no source code modification is required, right? So that same design that you would map in simulation, you can map across two FPGAs and meet the high-level protocol timings. Again, the high-level protocol timings being at the scale of tens of microseconds. So the latency of the inner FPGA interconnect is not a problem. And of course, also because this is a largely flow-through pipeline with a tiny amount of feedback here, you would expect that we would have no problem with feedback latency. Okay? So the second thing we're going to do with AirBlue is actually simulation. So often when we're evaluating protocols, we care about operating points at bit error rates of 1 in a billion. And of course, if you want to test that operating point, you need to generate billions and billions and billions of bits, which of course is a problem in software because the software simulator is running at kilobits. Now, of course, the FPGA is running at megabits, so by choosing the FPGA, we run 1,000 times faster. Now, of course, we can implement this on one FPGA, so we can simulate on one FPGA, and the question is, why would we want two? Well, the reason you want two is because the tools can actually find better implementations. So what we can do when we take a simulator and partition across two FPGAs, even if we worked on one FPGA, is get speed up. So here what we show is speed up relative to a single FPGA implementation. Most of this speed up comes from clock frequency improvements. So we just take the part under test, and we amp up its clock frequency as high as possible, and this gives us a faster simulator. Okay? So in summary, basically AirBlue and wireless pipelines in general are these deep pipelines with infrequent feedback. And at the protocol level, we only care about 10 microsecond timings. So this is an ideal solution to sort of take a prototype wireless transceiver and actually get it to work on the air. Okay? So now let's talk about something with a little bit more complicated communications graph. That is the processor simulator, HASIM. So what is HASIM? HASIM allows you to basically simulate complex multi-cores, so full cache hierarchy, out of order, and cycle accurate. So one key point about HASIM is that it's time multiplexed, which means that we don't, say we're simulating a 64-core processor, we don't lay out 64 cores. We lay out a single compute pipeline and multiplex it among all the cores. So it's like SMT. Okay? And of course, with that approach, it's very easy to parameterize the design for scalability. So of course, HASIM can go anywhere from 1 core to 10,000 cores. The question is whether or not you can actually implement it on the FPGA.
So I have to inject, it's not at all like SMT, if I understand what you're doing correctly. You're time slicing architectural state on the same underlying logic substrate.
That's right.
You're not dynamically provisioning microarchitectural resources among those time slices.
That's right.
It's much more like conventional Terra-esque multi-threading, if you're going to make a multi-threading analogy.
Okay. So anyway, it is multi-threaded.
Yes.
And of course, it has a complex communications graph with lots of feedback, right? So it's different than the wireless pipeline in the sense that all of these parts are communicating, and moreover, they're communicating almost constantly. Although the time multiplexing is going to help us cover some of the latencies. Okay, so what happens when we map HASIM to multiple FPGAs? Well, the first thing to notice is that on one FPGA we can map 16 cores, and then on 2 FPGAs we can map more than 100. Right? Again, this is because in HASIM, this time multiplexing means that we're not replicating the entire structure of the processor to add another core. We're only adding some state. Okay, so there's a big constant cost to building a core model, but the cost for adding a new core is not so high. And that's why we get this highly nonlinear scaling.
So just because I'm interested, if you look at a modern out-of-order microprocessor,
yep.
most of the area is devoted to the microarchitectural state, whether it's branch predictors, rename tables, reorder buffers, caches.
Okay.
And very little of it relatively is control state.
Okay.
So you have to multiplex all of that, and it seems like, as you add threads or logical cores, you're going to see a linear increase in all that state you need to buffer.
That's right, and we do. So part of I think the savings here is that most of these things are mapping down onto dense structures.
Right.
So it's not quite linear. There is some room to scale. So I mean, going from 16 cores to 100 for some of the structures means just stuffing more data into a VRAM.
Sure.
Right, and for many structures that means actually that they don't increase in size. Only some of the structures are increasing.
I guess if you have enough VRAMs to buffer all of the state and then scale up to large numbers of cores, then that works fine. I'm just surprised that that's the fact, given cache sizes and all of that.
So in HASIM, there's so remember, HASIM is a model, not an actual implementation. So much of the cache state is stored in an interesting way. So we actually synthesize a cache hierarchy. And so this hierarchy actually goes out to host virtual memory. Okay, so if, in some sense, that cache hierarchy is fixed for any choice of cores. Right? And the pressure on it, of course, changes, and its performance will change. The more cores you have, the more misses you will take. But the size in terms of FPGA area is not changing.
Right.
Okay. Yep.
Virtual, meaning you are using DDR3?
Yes. So I'll actually talk about how the memory hierarchy works in detail in a few slides. I think it's actually very interesting. But we'll get there in a couple of slides. It looks like we've got plenty of time to do so. It's actually the first talk that I've made it this far in this amount of time.
So before you move on, if
Yeah.
you have time, what are the different dual FPGA bars?
So again, we mentioned that as we add cores, we increase the amount of implementation area, but that has impact on clock frequency. So the more things you try to stuff on the FPGA, typically the worse that the tools do. Again, we're not we're just naive users of the tools. We're not trying to floor plan everything, right? So we just take whatever frequency is given to us by the tools. And so basically what happens is, let's take this bar, for example, right? So this is, say, 36 cores, right? So either a maximum 64 implementation or a maximum 128 implementation can handle this model. It's just that because the maximum 64 implementation is smaller, you get a higher clock frequency, and so you get some performance benefit as a result. Okay. So one last thing to note is how much performance we lose going from one FPGA to two FPGAs. So basically, it's these two bars here, right? So the gray bar is a single FPGA implementation. When we go to two FPGAs, we lose at most maybe half of our performance. Okay, this is already much, much better than the traditional tools, which would lose maybe an order of magnitude or more in terms of performance. Okay? And of course, as we scale the number of cores, we can cover more latency, and so our performance comes back up. Right? So in summary, single FPGA gets filled at 16 cores. But with multiple FPGAs, we can go to 128. And actually now we're trying to build a 1,000-core processor on some richer, yes?
So you mentioned at the beginning that there are commercial tools. Have you tried this on some?
We've never attempted to run the commercial tools, in part because we think that that's going to require major surgery. So the commercial tools are not quite so easy to use. They usually require that you do some modification to your RTLs. Anyway, so, and also, of course, you have to buy a box that costs a lot of money. The emulator boxes are not cheap.
I was assuming Intel might have helped you there.
Yeah, I mean, we talked about it and then we decided, you know, it wasn't a productive exercise. Yeah, yes?
So in some sense, your previous graph here is it's not necessarily the way that people might sort of approach a system and sort of make that is that first they have a throughput requirement, and then they build hardware to meet that throughput requirement.
Sure.
This is sort of cloudy, making that sort of design space a little bit cloudy because of the fact that you have multiple axes. How would you see somebody using the system if they said, okay, this?
So I'm a big believer in getting a system to work and then understanding its bottlenecks before trying to optimize. So I mean, yeah, you have a throughput target, but it's very hard to know where bottlenecks in a system are, particularly a new system, without actually having something working. I view this tool as first and foremost enabling implementation. So it's entirely possible that we'll get something to work here and we'll discover that there's a bottleneck, right? Where the bottleneck might be could be, I mean, my feeling is probably, the compiler is not going to produce the bottleneck, that there'll be some intrinsic bottleneck either in the inner FPGA throughput or maybe in memory or something like that. And then we go solve that, right? That's just my approach to problems in general, is get something to work first and then debug later. So I also asked the question, if we have this requirement of running all these channels between FPGAs, would the architecture that you hand code be substantially different from the one that the compiler is producing automatically for you? So I think that's another way to look at the problem, right? And I think if you consider it that way, the answer is probably not. That, you know, at the end of the day, you're going to be building this router infrastructure anyway. It's just you're going to have to go through the pain of debugging it by hand. And moreover, if you make any slight perturbation to it, you'll have to rework the whole system, right? So it may be the case that you can do the kind of longest job first optimization that I'm advocating, but I'd hate to have to write that code myself. Something like that.
Yeah, but how much you need to redo on the driver, what you call the driver? If I give you instead of B3 another machine, how much work you need to do?
So it's actually very simple, right? So we abstract that layer as just being a FIFO. So if you look at, for example, the so we use these high-speed inter-FPGA transceivers, right? So basically, all we have to do is get the core code, test it out, make sure it runs, and then abstract it as a FIFO and feed it into the compiler. So actually, it's quite straightforward. If you look at something like PCIe, right, going between host and FPGA, that's a little more complicated, but at the end of the day, it's still a FIFO as well, right? And it's just multiplexing on top of that FIFO. I mean, at the end of the day, if you look at the drivers that you're writing, this is what they look like. And it's not clear to me that you're going to do better than this. Although, of course, if you are doing better, there's probably a way to generalize what you're doing and feed it in here, right? I mean, generating router is just a phase of the compiler, right? So you could easily come up with a new router architecture and test it out, right? Again, that's the advantage of the compiler, is it makes things like that easier anyway. Okay, so now let's talk about resources in multiple FPGAs. So I'm going to talk a little bit. So again, right, I mentioned this at the very beginning, if you remember all the way back. What we get when we get more than one FPGA is access to most obviously more slices, but we also get more access to memory. Okay? And there's this analogy to multiprocessing here, right, where if we have 2 cores and 2 threads, right, both threads get a full cache hierarchy of their own, or at least parts of a cache hierarchy, and so they run faster. So what we need in the FPGA is an abstraction to sort of allow our FPGA programs, our HDLs, to exploit these resources. So we need an abstraction layer between us and the physical devices. So what I've shown you to this point is an abstraction for communications, right? These channels abstract the communication between FPGAs. Now I'm going to talk about abstracting memory in FPGAs. So basically what we've got is this very simple interface, and this is how we'll do memory in our designs, right? So just like a BRAM, you've got read request, read response, and write. So a very simple interface, right? Is that clear to everybody? So a few points about it. One, we have an unlimited address space, right? So this will permit us to specify any size we would like, even if that size doesn't fit on an FPGA. So if you specify 32 gig of space, you probably don't have 32 gig of DRAM. You can still write that down. And we'll provide a virtualization infrastructure to back that storage space.
The freedom to run as slow as you want.
Sure.
It's expensive.
Okay. You also have arbitrary data size, of course, right? So again, it's a parametric interface. So if you want 64-bit words or 36-bit words, we'll generate the marshalling logic for it. Okay. And then finally, again, as I've said before, it's latency insensitive, right? You aren't writing your program assuming that there's going to be some latency that you get between the read and the some fixed latency, right? So you actually write your program in a way that can basically decouple the read request and read response. Okay, so how does this look on a single FPGA? So what we'll do is each one of these are a memory client. We'll aggregate them all together on a ring and feed them into the onboard memory. Okay, so the first thing you'll do is have an L1 cache here. Okay, and if you miss out of the L1 cache, then you'll go to the onboard memory, which will be in DRAM or SRAM, depending on your board. And finally, if you miss out of that cache, you'll go to host memory. Okay? So host memory is what will take care of this arbitrarily large address space, in the case that you need it. Huh?
Host memory as the PC or
We'll assume that there's a server attached.
Or so it's not local DRAM attached to the FPGA.
So we'll use the local DRAM as an L2 cache.
I see.
Right. So basically, the flow will be something like this. You'll make a request to your local DRAM cache. You may miss. Okay? If you do miss, then you'll scurry off to the board level resource, which will be shared among all the boards. Okay? If you miss there, then you'll go back to host virtual memory. Okay? And again, it depends on your address space, right? And how big it is and how much data you're accessing. But again, the point here is if you need the large address space, we give you the ability to describe that. If you don't need it, say you say, I need an aggregate, a giga of memory, you will never miss in this cache, for example. Okay?
What is the use case, the motivating use case for a system like this that would be going down to
Well, I think the most obvious use case is portability, right? So that's the first thing, is I've given you an abstract interface, and I can build you a memory hierarchy on any board you want to implement on, including a board that doesn't even have memory, right? The problem comes in hardware designs frequently when you bake in assumptions about the underlying infrastructure to which you're mapping. And then suddenly that infrastructure gets pulled out from under you, either because you build the next generation, or maybe because you have to do something like move between boards. And at that point, if you've baked in some timing assumption that isn't true anymore, you've got to rework all your code. And that's a big problem. Now, again, you're trading something for the abstraction, perhaps, right? We're introducing all of these layers, so maybe you add a little bit of latency. That's certainly true. But the latency and the various performance loss comes at what I view is a very important price, the price of abstraction, right, and portability. So I can frame a design in terms of these caches, and as long as the platform, whatever FPGA it is, it doesn't matter if it's Xilinx or Altera, or what generation it is, I can run that design on any board. And that's pretty powerful.
From a portability standpoint, yes, but if
Right.
you are going through the effort of baking this into the hardware, making some fundamental assumptions about the resources available to get good performance out of it kind of is I would hope, a first line item.
So again,
is trying to develop this system.
yes, again, right, performance is critical here, right? And I don't know that we're trading a lot in terms of performance. Of course, I haven't ever done the study. But again, I can tell you, what would it look like if you were doing this yourself in hardware, right? Would you have an L1 cache here? Maybe. We also have a way of eliminating the L1 cache, so if you want to go directly to the DRAM, you can certainly do that. We give that as an option.
Contrast this to Andrew Putnam's thesis work in his ISCA 09 paper.
No, not having read those things, I can't.
Okay. He was synthesizing caches out of onboard DRAMs.
Right.
And distributing them around the chip. I don't remember if he went to an L2.
I don't know.
Yes, worth looking into.
Right. So anyway, I mean, you know, whatever technology you have to generate L1s is certainly useful here. I'll say that much. But again, the idea is that we're providing an abstraction layer. And that's going to be important. Oh, again, right, unlimited address space, right, fast local caches. And what happens when we map a design across multiple FPGAs, right? So here two things are happening, right? Again, when we have multiple FPGAs, the boards may be homogeneous, and then again, maybe they're not. So we want some portability of design, right? I mean, intrinsically, we've already said we're going to have multiple FPGAs, so we expect asymmetry, right? And in fact, we may not even know what pieces we're mapping to what boards. So it doesn't make a lot of sense. You know, the more you fix a piece of a design to a board, the less of this automation that can actually happen. So what are some cases that can happen here? So one, we automatically route clients to the nearest cache, even if it's on a different board, right? So here we have clients that are sitting on a board that doesn't have an L2, and they will simply route to the local L2, the closest one, even if it's on another board. Okay? Yeah.
So inherently, so you have all these VRAMs on the FPGA.
Yeah.
Each of them have 1 or 2 ports. Why do you want to build a central cache as opposed to a distributed cache? Each of
right. So remember that each of these clients has its own VRAM L1 cache, and those things can soak up all the resources on the board. In fact, we're working on an algorithm now wherein we do area estimates for placement. So we place design on board. We look and see how much VRAM is available left over after the user design, and we just scale up all the caches to soak it up.
When each client has, you say when you say each client has a cache, is that a single cache?
Yes, a private L1 cache, each one.
But still, I'm trying to understand why don't you want to have. So in a processor, there's a single cache because you want to have limited number of ports. But if on an FPGA, there are already these VRAMs baked in with all these ports.
Mm-hmm.
Don't you think that having a single cache as opposed to multiple ones that you can access in parallel is...
That might be a fine
basic.
architecture. So if I understand you correctly, you're asking, why is it that I don't just give each one of these guys a place in a shared chip-level VRAM cache? In fact, that's one option, right? We do have a VRAM central cache that you can use. Of course, the scalability and clock frequency issues there are pretty obvious, right? That is, once you have a resource that's being used by a bunch of guys, the multiplexing logic can be problematic. But that's a perfectly valid implementation. We'll lay you out a half meg or a meg of VRAM cache, and you can use that as your shared L2 if you'd like, right? But again, you'll never get the clock frequency to that you can get to the local caches, right? I mean, if you have to run wires all over the chip, you've got to run wires all over the chip, and it's going to be slow. So there's that trade-off to be considered too. And as I mentioned, we do give an option wherein you can disable the L1 caches if for some reason you don't want to pay the latency. For example, if you have a streaming workload, or you know that you're never going to hit an L1 for some other reason, you can just eliminate that cache.
Is it safe to say you've punted on coherence?
At this point we have. So these are independent address spaces. Although what we're working on now is, so ideally, let me tell you how coherence works in my mind. If I can just get the junior grad student to work on it, right? So basically what you would do is when you say scratch pad, you would also specify coherence domain. So you would say, I want this set of scratch pads to be coherent. And then you would synthesize some directory-based protocol on top of those specific scratch pads. Again, the approach is automatic synthesis, right? But it would most definitely be some kind of directory-based protocol, sharing the space. Again, in the applications that we're considering, primarily being these DSP algorithms, although HASM is starting to run into this coherence problem now, which is why we're speccing it out. Because what we want to do is basically slice that thing across 16 FPGAs, and of course then suddenly the functional memory has a coherence problem, right? And so we will be synthesizing coherence algorithms soon, I expect.
So the design space exploration sort of been mentioned before. I mean, that's a highly manual process. Could you see? Is there some sort of, I don't know, plan that you can see moving forward to try and automate that, or is that something that
to automate design space exploration? So in some sense, what I just described to you with inflating the cache sizes is in some sense that design space exploration constraint to the memory subsystem. So I think if you could express parameterizations and maybe their relationship, you could look to maybe have some machine assistance. So if the compiler throws down an algorithm, and that algorithm has some parameter by which it could be scaled, and it turns out that there's area on the FPGA, we could easily scale it up. So generally speaking, I think modeling this as some kind of linear system, or I mean, I don't know if it would work as a linear system, but that's how I would approximate it. Something like Pecora, this thing out of your colleagues down south, I think is an interesting approach to this idea of allocating area to different pieces. But yeah, I mean, if the compiler knows how to scale, then certainly it could maybe have some assistance in that. All right, so anyway, what do scratch pads do? So basically, like a processor architecture, I'm sure we've all seen this diagram before in general purpose processors. We have a bunch of plateaus. So we have some plateau at L1 where we get lots of hits. So this is stride versus working set size, right? And up is bandwidth, so up is good. So these values are hitting in the L1 cache, and then we kind of we have some region where we're hitting in the central cache, and then some region where we miss out to host memory and our performance sucks. But it still works, right? So just like in a processor, if you have to go page, then your performance will be horrific. And that's just the way it is. So write programs is good locality, I guess. Oh. All right, so what else can we do with memory? Sorry, does somebody else have a question?
So going back to that previous diagram, why is the stride? Why is there are low points and high points as you go to the stride on that? Yeah, on that very last.
Right, this divot here.
Yeah. So all of those divots.
Okay, so this divot comes from the way in which we do our L1 caches. So we actually do skew caches, and unfortunately, with skew caches, sometimes you get collisions, and some of the stride patterns produce pathological collisions in the skew.
When you say skewed, you mean skewed associative?
No, these are direct mapped. So skew associative direct map caches.
That sounds like an oxymoron. So what is the skew?
We hash the addresses into the cache. We just do a straight hash.
Well, any cache is hashed.
Yeah, but it's not a linear hash, right? We do some XORs. Right, so there's some hash function perturbing the index of the cache.
Okay.
Yeah. So it's a skew cache.
Yep.
Right.
So you know, in the literature, the benefit of doing skewed associative caches was reducing the probability of hot sets. Mm-hmm. And why would you make a skew function rather than a standard, just grab the bits hash function?
Well, for a simple reason, actually. So if you do that in HASM, wherein you're doing indexing based frequently on some processor enumeration, it can be the case that you actually do get a hot set on a single block in the cache, right? So you still have a hot set in these things, right?
Right.
It's just one entry, right? So if you have many addresses hitting the one entry, right? So we just want to provide some randomization there. That's all. Although we are now working on doing set associative L1s. But we'll still do skewing there too. Okay, so anyway, that's how this works. So now, we mentioned that we get more memory, so we can actually increase the size of the cache, but we can also introduce new algorithms. So one of the things that we can do in terms of introducing new algorithms to a memory hierarchy is adding prefetching. Right? Again, we're optimizing under the memory abstraction. So the user says, I have this read request, read response, write interface, and the job of the compiler is to soak up FPGA resources to make that thing as fast as possible. Okay? So what we're going to do here is add prefetching. So how does that work? So if we remember back to architecture class, right, you have some table, right, which you index into based on PC. And then if you have sort of a stride, right, so a stride pattern on a particular PC, then you'll try to prefetch out in front of that stride to get a new value to cover some of the memory latency. Okay, so we can do the same thing in FPGA. Although there's one key difference, and what key difference is that? Anybody? One of these fields is not right. There's no PC, right? So there's no PC in the FPGA, so we can't use that as a hint. Okay? So it turns out that hardware programs don't have a PC, which might make prefetching a little bit more difficult. However, balancing this difficulty is the fact that hardware programs have a much cleaner access pattern, right? So if you think about how a software program works, right, you're passing data through the stack, right? You're constantly inserting new accesses to memory, which really have nothing to do with the data flow of the program, and everything to do with sort of like stack frames and function calls, right? And so that could screw up the prefetcher. But in hardware, of course, we don't have that problem. Right? It's just a clean access stream. So even without PC, we can actually do a pretty good job of prefetching. Okay? And again, the idea here is if we have extra resources on the FPGA, we can add more complexity at the compiler under the abstraction and hopefully get more performance. So how does that work? So basically, here we have an implementation of matrix multiplication, and this is runtime normalized to an implementation without prefetching, right? And so, of course, here we do matrix multiplication, which has a very predictable access pattern of the kind that a stride prefetcher should do a very good job with. And we find that depending on the size of the matrix multiplication, size going this way, we actually get a lot of performance benefit with prefetching. And again, this comes because the original hardware wasn't doing a very good job of handling the edge cases in the matrix multiplication algorithm. Right, of course, as the matrix gets larger, the edge conditions are less important, right? We spend more time running down the rows, and so the benefit of prefetching is much less, although it's still measurable. Okay, but for small matrices, 64 by 64, the performance gain is enormous. Again, because we hide the latency. Okay, so that's great. So matrix multiplication, we should obviously be able to prefetch. So what happens with H.264? So H.264 has a data-dependent access pattern, still predictable, and we do pretty well here. Again, we get a maximum of about 20% performance gain with prefetching. And again, these are codes that have existed for many years. We wrote papers about them, and we're just using them as workloads. Again, because we frame them in terms of the memory abstraction, we can actually extract performance as we improve the algorithms in the cache hierarchy. Okay? So in conclusion, latency insensitive channels enable automatic multiple FPGA implementation with minimal user intervention. And when we do such an implementation, we can get higher performance, better algorithm scaling. And although I didn't talk about it, we get faster compilation. Okay? And the conclusion here, the high-level takeaway, is that high-level primitives can offer powerful automatic tools. Right? And as we move to more complex systems, these kind of tools will be necessary. Right? They can no longer be in the purview of the hardware designer to produce these implementations. Future work, so place and route. So as we know, those of us working with FPGAs, place and route is taking a long time, and it continues to scale up as the FPGAs get larger. However, the latency insensitive modules provide a way of dealing with this in that you can place and route the latency insensitive modules independently and then synthesize a network between them. The general idea is that long wires with long latencies, which you would get if you do this sort of distributed approach, can be broken with register stages, much in the same way that we use buffer boxes in ASIC process. So additionally, right, if we only have to recompile a part of the design, then network resynthesis should be cheaper than full chip resynthesis. Okay? And then finally, hardware-software communication. We already do this a little bit, but I'd like to formalize it a bit more. So again, the problem with hardware and software communicating is that software is this non-deterministic thing in terms of timing, but generally speaking, the latency-insensitive channels allow us to capture this. So basically, you could have latency-insensitive channels in software, latency-insensitive channels in hardware, some ensemble program composed of pieces of software, pieces of hardware, and we would synthesize all of the communication between them. So that's how that would work. And with that, I'll take questions.
Okay, thank you very much. Since we're at time, we may have time for one question or one or two questions, and if not,
This is more of a comment. You started out motivation saying that FPGA are useful for application, and yet you spend 99% of your time talking about processor simulation and architecture.
Processor simulation is an application for FPGAs.
No, because it doesn't talk with PCs and the way you left.
No, it absolutely does.
Hardware software interface.
No. No, so let me explain to you more of how HASM works, right?
No, I'm just giving you an impression from what we do and what you've been talking about. There is a disconnect. And you're into architecture, and we are more, I don't care about caches. Caches don't do nothing for me.
Well, maybe they do and maybe they don't. I mean, it just depends on what your access pattern is, right?
What I would like you is to see, for example, I don't know, something on visual or something that has high data rates going through, and see, and then you get into time constraints, multiple clock domains.
Well, all of these things have multiple clock domains, right? I mean, all of these implementations are multiple clock domain. In fact, what is nice about this approach is actually, once you have a latency insensitive module, you can pick a clock for each module, right? If it's beneficial, right? Again, you know, synchronizers change the timing behavior. So actually, this model kind of supports intrinsically multiple clock domains.
You spend all your time on time insensitive and as fast as possible applications.
Sure.
You know,
well, I think AirBlue is actually timing sensitive at the high level, right? Because you have to produce a result in 10 or 20 microseconds, and then it's a question of whether or not the latency between the FPGAs is tolerable. Same is true in H.264 decoder. I didn't talk about H.264 mainly because I think the results are not terribly enlightening. They're no different than the wireless transceiver. I mean, the basic idea is, yeah, we can partition a design. Yeah, the bandwidth between the chips is sufficient. And yeah, we meet the millisecond or whatever timing, even with introducing this new latency component. But I think what is different here. Let me address the processor simulation problem. So understand that the processor simulator is actually a hybrid design, because of course we're not modeling things like disk. We're not modeling things like most of the operating system on the FPGA. Actually, that stuff is running in a software simulator on top.
Been there, done that.
Right.
I understand. Yeah, you can do that. The reflection is more like all of that work puts your mind into a certain set of problems, and then when you actually have an application with specific time requirement, latency, etc., you end up fighting a whole different set of problems. With the tools, you get much closer to the tools. You get to understand UCF constraints, and then you get mid-timing is your big bugaboo when you spend a lot of time, and then the difference between synthesis, simulation, and the actual chip run becomes a problem, mystical problem set. So that's more my reflection. You phrase it as this is good for application, but in fact you talked about ASIC synthesis to a large extent.
Well, I mean, I only talk about ASIC synthesis in the sense that this is what multiple FPGAs were used for in the past, right?
I think more of the point is that ASIC represents a single data, a very specific application.
Sure.
Yeah. And many other applications, and with a certain set of constraints and a certain set of sort of characteristics, and there are many other applications that have different, widely different constraints.
Sure,
and
absolutely. Absolutely.
System level behavior, bandwidth level behavior, that type of thing.
Sure, I don't doubt it. I would think that this would accommodate of those designs, though.
I mean, I think as we move forward into more automation, I think it's really important to understand these different spaces and think carefully about. I mean, that's an easy statement to knock off, but there's a lot of FPGA intuition in the room that's not lining up with the approach that you're taking for many problems. So I think we should. Sure. It'll be important to understand those spaces going forward, and they may or may not.
I mean, if you have to do things by hand, you have to do things by hand. I mean, you know, sometimes we have to write assembly too, right? And there's nothing in this that prevents that. It's just that if you can get away with not doing that, then it's probably best that we stay at the high level. But of course, you know, can't always live in that world.
And by that, it's more like you brushed off the design space operation. And in practice, I don't know, when you have 10 hours of turnaround time, proposing that you make a run and look at that and do another run, it's fairly time consuming. So you would spend more time into doing area estimation, for example, as opposed to say, go ahead and synthesize and see what happens. Or reusing as much as possible. See what I'm saying? There's different kind of things that get in your way than if you're doing something else.
Sure, I mean, I completely believe it. Anytime you use the compiler may always be bad. But I think the lesson of history is that compilers inevitably get very good.
I'm all for compiler. I'm saying I would like to see more of compiler support in what you've done.
Sure. I mean, I completely agree that there is more work needed here, particularly on the quality of service front. But I think it is possible to model some of those things in the compiler and get good answers. I think. I mean, at least I think so. But we'd have to look at particular applications before we could get some conclusion.
All right. Thank you very much.
Nope.